check. All right. Check.
Okay. Okay. All right. Sorry about that. Technical difficulties. I think we're ready to get this thing started though. All right. Everybody hear me okay back there? All right. Excellent. Thank you. I appreciate that. All right. All right. So welcome to Bureau of the Scientist. So my name's Levi Beverly. I started Bureau of the Scientist back in 2014. We've been doing this almost every month, except COVID, damn COVID, but mostly every month since then. I think we're almost up to about 70 talks. I've given only a handful, 6 or 7. I actually wasn't scheduled to give tonight's talk, but my original speaker kind of backed out on me at some family obligations, so you're stuck with me tonight. So I'm a cancer biologist. I work at the University of Louisville. I run a cancer research lab, and I have a bunch of administrative positions within the Cancer Center. I started doing cancer research in 1998 when I was a junior at the University of Cincinnati. I've been doing it ever since, and basically the month I started working in a lab, I knew it's what I wanted to do for the rest of my life. And so everything I did up until then is basically how I got here, where I'm at. So I just want to point out that the only really way that besides flyers here at Holsapple that I communicate and I get the word out for Bureau of the Scientists is Facebook, Louisville Underground Science. You can find us there. You can see our picture that you should find there. And I usually only post Bureau of the Scientists and other similar things, maybe something that might be exciting that's happening in Louisville. I have a couple pieces of housekeeping information before we get started. So Olivia is your bartender inside. Please, when we're done here, make sure you cash out any close your tabs. We may have been here for a couple hours by then. Just make sure you take care of her. Appreciate that. Take your empty glasses and just sit them on the bar if you would. That would be amazing. I should say that I don't have anything to do with Holsapple. I just love Holsapple, and I will tell you that 25 cents out of every pint that you guys buy today goes to the Cancer Center to support cancer research. So thank you very much, Holsapple, for that. Upcoming technical difficulties. All right. This is not my first time, I promise. Okay. All right. So we have upcoming Bureau of the Scientist book. If you want to go ahead and bookmark that on your calendar or follow us, Louisville Underground Science. September 7th, we have Joseph Chen. He's an assistant professor in the bioengineering department at U of L. He uses microscope techniques and other bioengineering techniques to understand how cells, not just cancer cells, but other cells interact with their environment and talk to one another. Should be cool. I think he's going to have a lot of cool videos and microscope images from his lab. October 19th, we've got a medical doctor. His name is Jordan Higgleford. He's a sports medicine expert, and he's going to talk to us about mental, physical, and nutritional importance in injury prevention, especially in young athletes today. And then I hope, I haven't got this confirmed, but there will be one on November 9th. And the person who was supposed to talk today, who's actually given 3 Bureau of the Scientists previously on different topics, Lee Dugatkin from the biology department is going to talk. And he always gives an amazing talk. He shows up in costume a lot of times. He publishes books, like most of us publish 5-page papers. He will be doing a book signing while he's here. That should be a really good and fascinating topic. One other just shameless plug. I also do one other thing here at Holsapple that helps to raise money. This time it's for the Cancer Center again. But we run a trivia night. So August 23rd, it's $20 for a team up to 6. We've been doing this every other month for about 2 or 3 years now. A friend of mine, Alan Balderson, we rotate the charity that goes to. This time it's a Cancer Center. We do options for individuals, which helps people with mental and physical disabilities in the workplace. And we do VA Rep, which is Veterans Association of Research, Real Estate Professionals. Sorry, they help veterans with housing issues. Okay, so it brings me to our topic of the day. Breaking down National Geographic's top 7 stories, most exciting cancer stories of 2022. Okay, so like I said, I'm a cancer researcher. I've given a number of Bureau of the Scientists talks, and they're usually cancer related, but I've given them on stem cells and other topics that I thought people might be interested in. And there's one of my cancer researchers in my lab walking in right now as well. But I wanted to do something different this time. So I came up with a brand new talk, and when my other speaker backed out, I just decided after I sent about 20 emails to other people, I was like, just Google searching, what's the most exciting cancer research topics that have come up in the past year or so? And I found National Geographic had a whole article on the top 7 most exciting stories of 2022. So I started clicking on these stories, and I realized some of these stories are like in the Atlantic or the New York Times or Slate, right? And I read these articles, and as a cancer researcher, I got to the end and I was like, I still don't think people, non-scientists, would understand why these stories are this exciting, right? It's really hard to distill some of this information down so that it's attainable and understandable for people who with non-science background. And I've been thinking about cancer and cancer research since 1998, right? So this is what I do, but I still learned a lot of stuff here. But I think in order to understand these stories in any articles on cancer and cancer research, we have to take 10 steps back. And I just want to make sure that when I'm going through these articles, what I'm going to do is I'm going to take questions between each article, so you don't have to remember your questions till the end. But I'm also going to try to give you enough information so that you understand, that even as a non-scientist, why this is interesting. But first, we have to understand what is cancer, okay? So cancer are normal cells that have gone bad. So for the most part, cancer is not something that comes from the outside. This is not, most cancers are not caused by viruses or bacteria or anything. So we can't eliminate the causes of cancer. It's your cells that have gone rogue and are now doing what they're not supposed to be doing, okay? Cancer is a multi-step process. It takes, in most cases, cancer takes 20, 30, 40 years for a cell to become a cancer cell, okay? You need these things called mutations, which occur to your genetic material, your DNA. You need a combination of at least 8 in humans to get a cancer. Every cancer is different. So you have 10 women that walk into the breast cancer clinic. They all have luminal type B breast cancer. Their combination of 8 mutations that led to those 10 breast cancers are going to be different. So each cancer is different. So this is a true complexity of why cancer is so complicated. Okay, obviously cancer is bad. It kills a lot of people every year. In the US, it's the second leading cause of death behind cardiovascular disease. And lung cancer is the worst, kills the most people. Doesn't have the highest mortality rate, but it kills the most people. And in fact, if you add up everybody in the US that dies from breast, prostate, and colon, which are the next 3 most common, lung cancer still kills more people every year. And so, what was I talking about with this whole mutations and this whole process taking a long time? So this is just a drawing of how a normal cell becomes a cancer cell. Okay, so it says there that cancer is all about mutation, so you need a change to your genetic material, your DNA. You have to select for that particular mutation. So that mutation that happens in the background of 2-3 billion opportunities, that one mutation has to lead for a selection of that cell. And then that cell has to expand, and then that process has to be repeated. So like I said, this has to happen at least 8 times in humans, less times in lower organisms. So what I have here on the left is a cell. You can see by the color, the dark color, that cell got one of these mutations, okay? So over time, maybe that mutation doesn't do anything, but now that same cell gets a second mutation. And so now that cell has a selective pressure. So this is an evolutionary selective pressure, even if you want to think of it that way. And so now that cell starts to grow when it normally wouldn't grow, okay? Again, a cell within that population gets another mutation. It selects for, it expands and it grows, and so on and so forth, until on the far right you have what we call an invasive cancer. Okay, so this is a process. You might start here with this mutation in your 20s, but not end up out there until your 60s or 70s. Or you may never end up out there at all. Or if you inherit this first mutation from a parent, you get a pediatric cancer, right? That's why kids get cancers for the most part, because they inherit one of these bad genes from a parent. Okay, so I tell people I do cancer research. One of the most popular questions, the most common questions I always get is, why haven't we cured cancer? Well, my answer short to that is we cure lots of cancers. So 1930 and before, if you walked into the clinic with any type of cancer, there was over a 70% chance that you were going to die of that cancer. Today, this year, you walk into the clinic with any type of cancer, in general, there's a 70% chance you're going to live more than 5 years with that cancer, okay? So, obviously some types of cancer, that's not true. So pancreatic cancer, still less than 10% of people live for 5 years. Advanced lung cancer, 15% of people live for 5 years. But in general, all cancers, the hundreds of thousands of cancers, now, 70% of people walk in a clinic and they walk out 5 years, they live their life, okay? So I'm going to give you just one example of why that number went from 20% to 70%. So this is a type of leukemia. It's a rare cancer. It's called chronic myelogenous leukemia. Before 1982, if you walked into the clinic with CML, you were dead. So this is a survival curve. You're going to see these a lot. On the left-hand side is basically the relative survival, with 1 being everybody, 0 being nobody survives, and then on the bottom there's going to be a timeline. So this particular cancer, 14 years, or it's even less, so let's just say 7 years. 7 years after you walked into the clinic, there were basically less than 10% of people alive. Well, we developed new therapeutics, targeted therapies, and now, since 2001, since the therapy for this particular cancer, 92% of people live beyond 10 years with this. So this is just one example of how you basically went from a uniformly lethal disease to basically a uniformly survivable cancer, okay? And there are other examples of this, and the reason I point this one out is because this has to do with using your immune system. And this is going to be some of the hot topics that I'm going to talk about. So this is metastatic melanoma, okay? On the bottom left, I have survival curves. And you can see metastatic melanoma, and this is pre-2015. So we're talking only a few years ago. On the bottom, basically all of those curves, 20% of people are dead, or only 20% of people are alive after 4 months. This is a month thing, okay? But now what we've done is we've found ways to use your immune system to attack the cancers. And so what we've seen here now, it's hard to see the sun now, but if you see this top curve, our new immune therapies, basically 60% of the people were alive at 9 months of age and even out to 18 months of age. So we went from basically uniformly fatal at 4 months to 60% of people living at a year, okay? And this is just within the past 5, 6, 7 years. And this is the kind of things that we're seeing now that we've learned how to use the immune system to combat cancer. Again, I'm just pointing out that the bottom curve on the right is the same as the top curve on the left. We just learned to add one more therapy, and then we can push it up even further. Okay, so that brings me to the topic of the day. So what happened last year that got National Geographic excited, okay? And so this was the article, and then I'll have some references at the bottom if anybody's interested. But. Okay, so number one. Okay, I already mentioned this, COVID. So applying the COVID-19 vaccine technology to cancer research. So this article, was shown here, was published by the National Cancer Institute, and basically the title was, Can mRNA Vaccines Help Treat Cancer? Okay, so we've all heard this mRNA vaccines, we've heard a lot about vaccines, we've heard about COVID, we've heard about cancer, but probably not a lot of people have heard about mRNA vaccines and cancer, okay? And in fact, there's not a lot of vaccine and cancer information or studies out there. Okay. Okay, so you read this, you're not a scientist. There's a couple questions that you have, right? A, what exactly is a vaccine? What's the difference between an mRNA vaccine and a normal vaccine? How can we use this for cancer, and how can something that's killing viruses be used to kill our own cells, right? Okay, so first thing we got to kind of step back and look at is, how does a traditional vaccine work? Okay, so we've all gotten flu vaccines, maybe polio, maybe whatever, measles, mumps, whatever they are, right? But so the basis of how all traditional vaccines have worked in the past is that you take that virus and you kill it, you do something to it that inactivates it, you inject that into your body's immune system makes antibodies and ramps up all these cells in the body, and we're going to go into these cell types a little bit more. And then those cell types and those antibodies destroy that thing that you're trying to kill, okay? And so this is always dependent on making large amounts of these actual viruses and then figuring out ways to kill them that makes them not infectious anymore. And then going through this process, okay, so how's an mRNA vaccine different? And what is mRNA maybe? Okay, so your quick molecular biology seminar for the day is, what's mRNA? Well, mRNA is what makes proteins eventually, okay? So this is the central dogma of all molecular biology. You have DNA in your system, which I've already talked about, every cell, it's your genetic material. DNA is turned into something called mRNA, or RNA, and that RNA becomes a protein, and the proteins are the functional units of your cells for the most part. Okay, so essentially now what we can say is that mRNA is what eventually becomes a protein if we put it into cells, okay? So, but just keep that in mind. So instead of putting a protein or a virus that's been inactivated, the mRNA vaccine technology is just going to start with this mRNA part and then let your cells do the work here, the rest of this process. Okay, so again, traditional vaccines are either killed viruses or pieces of viruses, and then they're injected into your body. But turns out that viruses and all cells use mRNA to make the proteins. They make the coat proteins. They make all the functional proteins. So what you can actually do is you can easily, in laboratories and at scale, you can make synthetic mRNA. And you can just inject that into a cell, and the cell doesn't know it's synthetic. The cell will just take that mRNA, go ahead and make protein right out of it. Okay? So the reason that this is important is because now what you can do is, instead of messing with these viruses and making them at large scale, you simply make synthetic mRNA in a laboratory and you inject it into a cell, and then the cells make these proteins of the virus. And so what these mRNA vaccines are is it's one piece of one protein of the virus. So there is absolutely no possible way that you can get COVID or any of these things from an mRNA vaccine. Like I said, it's one protein out of hundreds, and it's not even the whole protein, it's just a small piece. And so the reason that this was so exciting and that this was able to then make an impact in cancer biology is because the COVID pandemic showed for the first time that these mRNA vaccines can be made in the billions of doses, and they can be given to literally billions of people with relatively low or no side effects. And so before the COVID pandemic, mRNA vaccines had been worked on for decades and decades. So that's why they're actually able to be made so quickly and put in people so quickly, because they had already been studied, but not at the scale and not at the testing level. And so in 2023, there's 2 articles that came out this year. This one up in the top is from, it's either Science or Nature, which are 2 of the top journals. Basically what they found a way was to use the RNA from pancreatic cancer as a vaccine. And they had absolutely amazing results in this paper. And then in the lower right hand, you can see they're already starting a clinical trial. Just within a few months of this paper coming out, they're going to be trying this at Memorial Sloan Kettering Cancer Center in New York City to test these mRNA vaccines and their efficacy in pancreatic cancer. And like I said, pancreatic cancer is already one where if you can make any headway, any change in the survival curve of pancreatic cancer, it's going to make a huge impact in patients' lives. Yeah. And so I didn't go into all the details, but you have to know what that pancreatic cancer, the mutations in that pancreatic cancer are, and then you have to base the mRNA vaccine on that. So it would be a personalized medicine. So you would have to come in, we would take a piece of your pancreatic cancer out, we would figure out what mutations are there, and then we could make an mRNA vaccine to that. So it's very more involved than I make it sound, but it's a good question. And so anyway, I already mentioned that stuff. Okay. So I'll take 2 questions on the mRNA vaccine story, and then I'll move on, and then I'll take as many questions as necessary at the end. But if anybody has pressing questions on this one, I'm going to move on to the next. Yeah, sir.
So COVID was one of the best things that ever happened to cancer research.
I don't know about that. The question is COVID one of the best things that ever happened to cancer research? And actually, one of the last articles I'm going to discuss today would argue exactly the opposite of that, and for some very rare particular cancers. I think there's going to be many, many more opportunities for mRNA vaccines that weren't used previously just because of how well they were able to be made, the price of them, and the scale. I mean, there were 14 billion doses of the COVID vaccine that have been given out. So, okay? All right, so the next story involves, again, something that has to do with your immune system. And again, this is one of those stories where you had a cancer type that was very lethal, and then all of a sudden you could cure patients, okay? So this is called CAR T-cell therapy. Anybody in the audience heard of CAR T-cells? Anybody at all? Okay? A couple people. Probably scientists or people in the know. So CAR T-cells it stands CAR as chimeric antigen receptor. Okay, a lot of jargon. But the reason that this was in Science News, the reason that this was so exciting was because it was the 10-year anniversary of the first patients that were treated with this particular type of therapy. And the first 2, I don't know if it was the first 2 patients, but there were 2 patients that were treated very early with this therapy that were still alive at the 10-year mark, whereas previously they would not have been alive. Okay, so a lot of things that we got to kind of break down here. CAR and T-cell, okay? So first thing we need to know is, what's a T-cell? So a T-cell is a part of your immune system, okay? So your body is filled with what we call white blood cells or immune cells, okay? All immune cells start out as cells in your bone marrow, and then they go to different parts of your body, and they become, again, the sun's kind of blocking me out here, but they become any of dozens of cell types. This is really simplistic, okay? But these cells, they fall into 2 categories, either adaptive immunity or completely blanking. Somebody help me. Innate, thank you, God. Innate immunity or adaptive immunity. So either they attack things because they recognize them, and or they are already there and they attack things like bacteria and viruses and stuff. Okay. So T cells are one of these adaptive. And the T cells are what work for the most part because of your vaccinations, for example. Okay. T cells will recognize bad things and kill them. Okay. And so, but the problem is that in cancer and many other diseases, the cancers actually find ways to turn T cells off. Okay? So your immune cell system doesn't work. So the immune system is so important, not only in bacterial and viral and fungal infections, but in cancers as well, and keeping cancers at bay. So if we didn't have immune systems, we would all die of cancer at very early ages. Okay? We'd be walking tumors. And some of this can be seen with people who are immune compromised, like AIDS patients. They die of cancers that most normal people never die of because our immune systems keep those cancers at bay. Okay, so T cells are this critically important component of your immune system. They're able to recognize things and kill these within your body. Okay, and one way that they recognize things is by this thing called a T cell receptor and a bunch of other mumbo jumbo that's not important. What is important is that these T cells bind things like cancer cells, and they literally kill them, like directly kill these cells. Okay, and so what I have here is just a picture on the far side. And this is an electron micrograph of T cells surrounding a cancer cell, okay? And they would be killing that cell. I don't know if it's going to work. Let's see. Okay, so I have a, oh, it's not showing. Anyway, I had a little video, but I can always come back if we need. At the end, I can show it. But I had a little video of it was a microscope image of a T cell coming in, and it shows it binding to a cancer cell and then killing the cancer cell. Okay, so that's all well and good. So this doesn't happen under normal circumstances within a tumor, okay? Because the tumors find ways to shut the immune system down. So what scientists many years ago had found is that you could actually take a T cell out of a cancer patient's body. You can put in a chimeric T cell receptor or a receptor to recognize what you want it to recognize. And then you can put those cells back into the cancer patient, and they'll find the cancer and kill the cancer patient. No, sorry. Cancer cell. They'll kill the cancer cell. And so what I'm showing here on the right is just a very simple cartoon of you basically take the T cells out of the patient, you put the gene that you want, the antigen receptor you want in there. It is now expressed on the T cells. The T cell goes around the body. After you re-inject it back in, they find the cancer cell and they kill the cancer cell. It's amazing, amazing technology. And again, this is just showing what I just told you. And so why was this particular paper so exciting? Okay, so this says Emily Whitehead, the first pediatric patient to receive CAR T cell therapy, celebrates her 10-year cancer-free survival. And there's a picture of her here in this article, and it shows all this technology and stuff. And so this is just one example of how I can imagine at some point 20, 30 years ago, this was like the most harebrained, crazy idea that a scientist ever had. Like, I'm going to take a cancer patient, I'm going to take your immune cells out, I'm going to manipulate it in my laboratory, and then I'm going to expand those cells, and then I'm going to put them back into your body, and then we're going to see what happens. Okay? And that's exactly what they did. And this is no small feat, and it's amazing. But this is one example of 10 years of this particular person surviving. But this is the kind of results here. Again, the survival curve. This is a particular type of lymphoma. As you can see on the bottom, that's labeled standard of care, SOC. So this is chemotherapy. You can see 20% of the patients are alive at about 18 months. But now if you add this CAR T therapy, you can see that at 18 months, 60% of the patients are still alive. So again, this is an amazing finding, and this is amazing, and it's really helping patients. Okay, so what's the downside to this? Like, why are we just doing this for everybody? Well, the one downside is you can only make these chimeric antigen receptors to a very small number of things. So they work really good on specific types of lymphomas and leukemias, but they are not able to be used broadly yet on all types of cancer. The other problem is, as this article says, the treatment costs $1 million. Okay? So that's the actual treatment, and then the post-care follow-up treatment is at least $1 million for this. And so, you know, that's one of those things where probably figure insurance is not going to pay for everybody to get $1 million treatment. Is that $1 million going to be sustainable? How long is that going to get you, and is that worth it financially versus, you know, life-wise and all that? So that's a big thing right now. Like, this is just such a labor and laboratory intensive therapy. It's not like I can make 10 grams of a small molecule for $100 and just divvy it out, right? This is a super labor intensive issue. So, unfortunately, and you can't see it there, but there's only about 100 facilities across the country that can even offer this service. Like, most places do not have the capability to do this. Louisville is one. Okay, so I probably just keep going. All right. Scientists, so this number 3, scientists are unraveling how cells move in forming cancer therapies. And basically, I'm not going to talk about this one because you got to come to next month's Bureau of the Scientists. Like I said, Joseph Chen, that's what his entire laboratory is working on, so that kind of works out perfectly. I can skip this one and you can come back next month and learn about that. Okay, so this one is kind of one of those ones that absolutely blew my freaking mind. So this is one of the ones where I learned. I'm not a clinical scientist. I don't deal with clinical trials for the most part. I do read. I'm on the clinical trials review board, but as the scientist at the Brown Cancer Center. So this paper, and again you can't see it because of the sun, but it says it says diversifying the pool of clinical trial participants to tackle breast cancer. And the actual article says this clinical trial wanted to end breast cancer disparities, but first it needed to enroll black women. Okay, so all right, here. So these are some of the things that I find when I'm doing these, and it blows my mind. So 90% of all people who participate in clinical trials are white, okay? Only 40% of people who participate in all clinical trials are women, okay? Well, black and African Americans, they only made up 3.1% of all clinical trials, although they make up 13% of the population. So think about the genetics and the history and all this. You're trying to find cures and make things better for everybody, but you're not actually studying everybody. You're only studying one group of people for the most part. And so how can you advance the science and the treatments if you don't have people involved in the studies, okay? So, which seems like this should be an issue. This would be something that would have been figured out and solved a long time ago, but it's not, so unfortunately. And that's why this article that I mentioned was such a big deal, because they were trying to fix that problem. And the reason that this is important is because although it turns out that black women and African American women have a 4% lower incidence of breast cancer, they have a 40% higher death rate from breast cancer. So, and again, if these black women are not in the clinical trials, how can you know if you're treating them appropriately, or how can you move the clinical science forward? And they also have some other ethnicities on here, which again, this is amazing to me. And I had heard these things before, but yeah, to see them, it was crazy. So this was the article, Smarter Breast Cancer Screening Measures Risk Down to Your DNA. And there was a Time article on this group. Basically what they were just trying to do is make a huge, large clinical trial that had everybody represented to at least the extent that they make up the general population. And like I said, it doesn't seem like that should be something that would make a lot of news, but it hadn't been done before. How's that possible? I don't know. I'm not a clinical trialist, and I'm not a clinical scientist, so I'm not sure. Okay, article number 5. Cancer is linked to bacteria and fungi of our microbiomes. In the actual article that was in the New York Times, a new approach to spotting tumors. Look for their microbes. Okay? Okay, so what do we need to know? That's fun. What do we need to know about this? So it turns out that everywhere in your body has microbes. Bacteria, fungi, viruses. Okay, that might not be shocking. But it was actually thought for a long time that there were certain parts of your body and certain cancers and diseases that were what we call either sterile or microbe neglected. And so like your lungs were always thought to be sterile environments. Tumors were not thought to have bacteria and fungi and viruses. But it turns out, starting pre-2020, there were many, many papers that started to come out saying that if you take a tumor, no matter what tumor it is in the body, and you look for microbes, bacteria, fungi, viruses, you'll find them. Okay? And in 2022, there was a group that actually showed that fungi can now also be found within the cancer cells. Not just within the tumors, but actually in the cancer cells themselves. And they can be predictive of outcomes, and they can actually be predictive of your treatment outcomes, your treatment responses. And so how do we find bacteria or viruses or fungi within tumors? Okay, so this is actually a figure from a paper that my lab just published a couple months ago. And I know, again, you can't see it, but I'll walk you through it. Essentially, you take a biopsy of a tumor. In our case, we did lung tumors. So we had collaborators at the British Columbia Cancer Center up in Vancouver. And they had 70 patients that came in with lung cancers. The surgeons went in and they did surgical resections of the tumor. And then they also did slight resection just adjacent to the tumor. So you had what was quote unquote normal lung, and you had lung tumor. And then you do a process called sequencing, next generation sequencing, which I'll get into in a minute. And you actually can identify bacteria. You can identify the phyla, the species, all the way down to the class and the order and everything, okay? And this was something that was not really possible previous. So what are these other papers, these big papers? Again, what they found, this is an article from 2020, again in Science or Nature, said the human tumor microbiome is composed of tumor-type specific intracellular bacteria, meaning if they took breast cancer, they had one type of bacteria. If they took lung cancer, they had a different types of bacteria. If they took colon cancer, they had different types of bacteria. And so there's a graph down there, but it just shows the type of cancer and how many bacteria were in that type of cancer. And so like breast cancer, for example, had lots and lots of bacteria, whereas melanoma, skin cancer, didn't have as many bacteria, which is kind of weird because melanoma is usually on your skin and breast cancer's not. So, okay. This is just another same paper. Okay, so again, this is the paper that my lab actually published a couple months ago, and the title was Methionine-Producing Tumor Microbes Fuel Growth of Solid Tumors. So what our lab actually was able to show is that within the tumors, lung tumors, bacteria produce things that the cancer cells take up, and then in turn, the cancer cells produce things that the bacteria take up. So it's actually a symbiotic kind of crosstalk between the bacteria in the tumor and the cancer cells. And this is important for the cancer cell because under conditions of limited nutrients, the bacteria can actually give the cancer cells what they need to grow. And so now you can imagine that now we could come up with a therapeutic maybe that targets the bacteria within the tumor so that they can't do that anymore. And so another reason that these papers were so amazing is that we thought for a long time cancers were essentially just balls of cells. Okay, so this is 20 years ago or longer. Okay, so a cancer is just a ball of cells. Okay, and that's just the picture, again, you can't see very well, it's just the same cell in a ball. That's what a cancer is. Okay, well, years of research, it showed us that a cancer is actually more like a complex organ. It has dozens of cell types. So it's got the cancer cells, but it's got the immune cells. It's got what we call stromal cells. It's got blood vessel cells, so on and so forth, right? But now we take that one step further. It's got all that, but now it has bacteria, and it has fungus, and it has virus. And all of these things affect how the cancer cell grows, how the cancer grows, how the cancer responds to therapy. There was a paper that was published that said, in its particular type of cancer, if you had a particular bacteria type, the chemotherapy called gemcitabine was not effective because the bacteria actually metabolized the drug into a non-effective form. Like this is something we didn't even consider 10 years ago. Okay, I got 2 more stories left. Since I rambled on at the beginning, I think I got time. Okay, this one's actually kind of interesting. So this one was entitled Genomics Tools Applied to Dog Cancers. Okay? So, and the actual article was called The Scientist, and it says the pet health industry takes on canine cancers. Okay. So what does that mean? Okay, so a couple pieces of information. So during COVID, 1 in 5 households adopted an animal. U.S. pet owners spend right now approximately $118 billion a year on their pets, and that's expected to go up to $270 billion by 2030. Okay, so the pet care industry knows that people want to spend money on their pets. Okay, so how does this relate to cancer in dogs? Okay, so 1 in 4 dogs will be diagnosed with a cancer. In dogs over 10 years of age, 1 out of 2 dogs will be diagnosed with a cancer. Okay? So again, companies realize this, and they want to help the pet owners. So they've come up with tests using techniques applied for humans now to their dogs, and they're commercially available. Okay? So you can send off your dog's saliva or a small blood sample, and they can do a lot of these genetic tests that they do on humans, but they can do it on your dog. Okay. Well, how do they do this? Okay. So we need to take a step back again and get a quick technology and biotechnology lesson. So they use something called next generation sequencing that I discussed earlier. So what does this mean? What is next generation sequencing? Okay, so sequencing technologies were invented a long time ago, 1990s-ish. That's what we had for a long time. It was slow, it was very costly, but it was useful for doing small pieces of DNA, right? I said you have billions of base pairs of DNA in every cell, okay? So this thing called next generation sequencing, and again, I'm not going to go into the specifics of the technology, it was invented in 2007. Has anybody here heard of the Human Genome Project? Okay. So the Human Genome Project was started in the 1990s, and to sequence one genome cost over $1 billion. Okay. The first human genome, the first edition, first version, came out around the year 2000-ish. It cost $1 billion, and it was dozens and dozens of countries and institutions working on that. Okay? Next generation sequencing came out, new technology, in 2007. All of a sudden, you could sequence a genome for about $1 million. Okay? So $1 billion to $1 million. Well, guess what? I can take my cells out of my body right now, walk them down the hallway at U of L, and I can sequence my entire genome for about $400 now. That's how far the technology has come in a very short time. Okay? Analyzing your 3 billion base pairs of information, that's a whole different story. That's going to be another $1 million, not million, but a lot of money in information technology and time. But you can do it. And so these canine genetic companies, genomics companies, they do that. They do this next-gen sequencing. You send your cells from your dog. They tell you all the mutations that your dog has or whether or not your dog has cancer. Okay? It's all well and good. So this was a paper that came out from a company. It's called PetDx. Never heard of them. Don't know anything about them. This is not an endorsement. They have something called the OncoK9 test. They did this paper, came out, I don't know, a year or two ago. Essentially, they sequenced 1,000 dogs in a prospective study, meaning across the country, they had 1,000 dogs. They knew which ones had cancer and which ones didn't have cancer. They sequenced the genomes of blood, DNA they got from the blood, and they could predict with 98% specificity whether or not a dog had cancer. Again, this is they knew which dogs did and didn't. With only 55% sensitivity though. They did 85 different dog breeds, they did 82 different cancer types in those dogs, and it's about $500 that they can do this. Okay? So that's proof of concept. It's important to note though here, if you do this in a human, it has to be FDA approved. Okay? But for a dog or a pet, whatever, it's just all willy-nilly. So there's no legal, there's no regulations on these things, okay? So, again, this is a prospective trial, so they knew which dogs did and didn't have cancer, and so you have to take those specificities and such into account, sensitivities and specificities. So the other thing too is, okay, so you send your DNA off of your dog and he has a cancer, what are you going to do about that in most instances? Right? That doesn't really help you, unfortunately. I mean, we can do surgeries, and there are some cancer drugs that we can give to dogs, but for the most part, nothing you can do about it. So what do you do with that? And then obviously the last thing, again, that you can't see, is that the company recommends you do this sequencing once a year. So that's $500 a year right there. So that's going to inflate that $270 billion a year that we're getting to, right? Okay, so my last little story, the last article here is a little bit more kind of mentioned with the COVID earlier. this is an interesting story to me as well. So it says an immunologist championed the COVID-19 vaccines even after it exacerbated his cancer. It made his cancer worse. And the actual article was in the Atlantic. And the actual article said, did a famous doctor's COVID shot make his cancer worse? Okay. So, I mean, we all had heard at some point during the pandemic, some point during the vaccines and the boosters, somebody who knew somebody who knew somebody, or maybe you knew somebody who had a severe side effect or some sort of a side effect, right? This is an interesting case study because it's clear it did make his cancer worse. But it made his cancer worse because the vaccine did what it was supposed to do. Okay, so just stay with me for a minute. Okay, again, you can't read it, but I'll read the article. But so this guy actually, he was a scientist himself. His brother was a scientist. This whole thing happened, and he actually wrote a one-person case report on it, on himself. Okay, and it says the case report was rapid progression of angioimmunoblastic T-cell lymphoma following BNT162b2 mRNA vaccine booster shot. A case report. Okay, so clinicians write these things that are called case reports, and it's basically an interesting patient where something weird happens, and they just want other clinicians to know about it. But this article is actually fascinating because it went through the whole backstory of how this guy was an immunologist. He studied these things. He had this bad side effect. He didn't know if he should go public with it because the way that people react when they hear these kinds of things. Okay? So as you can see, maybe you can't see on the right, these were his CT scans. So suffice to say that on September 8th, he had a bunch of lesions from this lymphoma. He got a vaccine booster, and then 12 days after the first scan, he had many more lesions. Okay? So it's hard to argue that his cancer didn't get worse. Okay. Well, so step back just a minute and bear with me. So I already told you that vaccines work by activating T cells, making T cells more effective at killing what it is that they're supposed to kill. Well, the particular type of cancer that this guy had was a T cell cancer. Okay? And it turns out that this case report, this has happened in 2020-ish, there was an article that came out in 2018 where they used mice. And they were already modeling this particular type of cancer in mice and giving them essentially a vaccine. Okay? And what happened was these mice, their cancer got worse. But this was not a vaccine for COVID. What they were actually using in this particular example was sheep blood cells. So they were basically injecting with something that was foreign. That was the whole purpose, was just to ramp up the immune system. So these mice were predisposed to a particular type of T-cell lymphoma. They injected sheep red blood cells, antigens, and the mice got worse T-cell lymphoma. Okay? And it turns out that the mutations, and this is kind of getting in the weeds a little bit, but it's fascinating to me. The mutations that they gave these mice were the exact mutations that this guy had in his T-cell lymphoma. And so it's one of those things where you see something that incredible that happens in the clinic, and then it turns out that scientists were already trying to figure this out in the laboratory years before. Okay? And so basically it makes sense, and that's what this article goes on to say, is that yes, it made his leukemia lymphoma worse, but it's because the vaccine was doing what it was supposed to. But of course, this article comes out, and you have the people, I just took two quotes again from this Atlantic article. You have one person that came out, and all of a sudden they saw this, and they're like, the lymph nodes of those who have taken these shots are exploding, burgeoning, and bulging with this toxic bioweapon. Okay? This is one case report, not the people, you know. And the second one says, lymphoma, that's right, cancer of the lymphatic system. Stop this from getting into babies and children, right? So you can take anything and turn it into something that pushes your agenda. But then I also, at the bottom here, I have the guy we've been talking about, this guy, his name is Dr. Goldman. And at the end of this article, Dr. Goldman says, he remains adamant that the COVID-19 vaccines are necessary and useful for the majority of people, but he wants the discussion about vaccines to be transparent. So the reason he published this case report on himself is because he believes, like most scientists do, that everybody should get all the information pertaining to all subjects. You shouldn't hold information away. Okay, so now I'm going to leave you on a lighter note, now that I've talked a little longer than I wanted to. Some of my favorite science quotes, just so you know that where I come from. So your inability to grasp science is not a valid argument against it. Okay, Neil deGrasse Tyson. The good thing about science is it's true, whether or not you believe it. What refutes science? Better science. What does not refute science? Your feelings, your religion, your favorite politician, your half-baked opinion after watching 2 YouTube videos. And of course, Neil deGrasse meme, y'all MFers need some science. And with that, I'll take any questions. I will take questions about anything that you have. Yeah, actually, yeah. Yeah, that's a good question. So it's about quality of life versus quantity of life at the end. So I tell you that most of the, and again, there's exceptions to everything, but the vast majority of the things they're using your immune system or the small molecules, especially in the CML, they have way less side effects and the quality of life is way better than using the standard of care chemotherapies. So that, you know, the chemotherapies for the most part, which is what people kind of think about when they think of cancer treatments, everybody's known somebody who's gone through the regimens of chemo. You lose your hair, you're nauseous, you have no energy. Like, we're hoping to get away from that, but almost all of these things are still being used in conjunction with those. But if we can do only these, it will be better, but we're not there yet for the most part. There are examples of those, but for chemotherapy is still here to stay, because in some instances too, using the chemo first boosts the later immune response to the tumor. So yeah, so but for the most part, the quality of life is much better than it had been previously. Yeah.
Why does chemo work?
Why does chemo work? Okay. I teach lectures on whole classes on this, but so the short answer is chemo is poison. So we're talking about, you know, people have heard of like cisplatins and gemcitabines, things like that you get for most solid tumors. Like, they're poisons. They were found as poisons accidentally. Mustard gas, nitrogen mustard gas was the first chemotherapy ever used, and it killed hundreds of thousands of people in World War I, right? But now it's a chemotherapy. I'll tell people, I'm a basic molecular biologist. So one of the things that my lab really tries to understand is, why does a normal cell become a cancer cell? And when you understand why a normal cell becomes a cancer cell, you start to understand why these chemotherapies kill cancer cells, but they also kill normal cells. So it all has to do with the ability of the cancer cells so most of these things are DNA damaging agents, right? They kill normal cells, like I said. But the cancer cells are slightly more sensitive just because they already have so many things screwed up inside them. I mean, that's kind of the short answer. And all these new therapies are working because they're specific, more or less, for the cancer and not the normal cells. And that's kind of the dream, is that you come into the clinic, we figure out what kind of cancer you have, what the mutations are, we give you a cocktail just for that. So, yeah. Yeah, Rick?
I want to go back to the story about the microbiome of tumors. How common are these bacteria and fungi that you mentioned within a normal non-cancer patient, or are they present at all?
Yeah, so questions about the microbiome, the bacteria, viruses, fungi. They are everywhere. Actually, 1/10 of your body weight is bacteria and these things, right? So the number of bacteria in your system outnumber the number of you. So you're actually more bacteria than you are you. But so they're everywhere, and they play critical roles. Like, you have bacteria in your gut that can break down things that your cells can't break down, and you need those nutrients. And so there is a very delicate balance between the bacteria and the microbes within yourself that needs to be maintained. You know, so like people, if you take antibiotics, you might get a C. diff infection, which is bad bacteria, which have now overtaken the good bacteria. So they're everywhere. They're on your skin, they're in your nose, they're in your mouth, in your gut, colon, everywhere. And if anything throws that balance off, disease can come from that, whether it's colitis or, you know, even stomach cancers and things like that. So, and it's changed. And the point is that it becomes slightly different in the cancer. And like I said, is that because the cancer and the bacteria are talking to each other? So is it a direct correlation relationship, or is it a true but unrelated? And that's what we're trying to figure out now.
So mine was what you were saying. Like, is it the cause of it, or is it just there?
Yeah. I mean, in some instances, we know that if they're there, then it's going to be worse. Or if it's there, then you're not going to respond to a certain chemotherapy. But how did it get to be different? That's what we don't know yet. We know it's different, but we don't know why it's different. No, but I don't know that one. Okay. Okay. Now, I don't know. He's asking about a paper that came out. That maybe it might have a non-trade name or something. I mean, I'll look at it when you get done if you have the article up. A lot of times these things, they get multiple different names depending on which company is using them, and sometimes I have heard it just a different name, and sometimes I don't know everything.
Was there a follow-up about the fellow that the COVID-19 vaccine exacerbated his cancer? Dr. Goldberg?
So according to that article, and again, I didn't look into it tremendously, but he was still alive. Like, he went back into remission. So they were able to give him another round of chemo.
Okay.
But again, I don't know when that came out, unfortunately. Yeah.
In your field, what are some of the greatest challenges you've had to face?
In our field, what's some of the greatest challenges that we have to face? So I'll give you one example of things that I deal with, for example, is, so like I said, I'm a basic molecular biologist, like try to understand how does a cancer cell become a normal cell, and then can we figure that, use that to our advantage. So in recent years, the NIH, which is the largest biomedical funding agency in the world, National Institutes of Health, they've started to have more focus on what they call translational research. So that's research that can be used in a patient in the foreseeable future, like immediately or within a couple years. And so that's all well and good, and that sounds like that's something we should be doing. But the problem is that things that are being used in the patient right now, the groundwork was laid for that 20 years ago. And so one of my favorite stories is, so the guy that discovered, or the inventor, or whatever you want to call him, his name is Jim Allison, of the immunotherapies that are used that I showed, the immune checkpoint therapies. He won the Nobel Prize 4 or 5 years ago for those discoveries. And I saw him give a talk at a conference, and he got up, and the very first thing he said was, I just want everybody to know that we started out studying this because of the basic, interesting, fundamental biology. And that was in the 90s. We had no idea that this information was going to be used in patients 20 years later, right? And so that's kind of the argument for like why we still need to understand things at the basic and fundamental levels, because you never know what's going to be the big thing 20 years from now. You know, it's easy to catch a wave and jump on it at the top, but all these fads and waves crash, and so we need to know what's going to be the next thing. So I would say that's probably one of the biggest things, at least for me in my lab, is trying to get people to buy into why what we're doing could be important in the future. Yeah?
With the digitization of medical records and the whole crowdsourcing of all kinds of different things from Google Maps, Social Lego, have you guys seen it in your field?
So the question is about the digitization of medical records and crowdsourcing. I see articles all the time on like a question that gets crowdsourced, especially when it pertains to maybe like a protein structure or a protein function, and then you get all these people that jump in on it and they figure it out because of the masses. And I mean, short answer is I don't know anything about that really, but it is interesting because, as far as medical records go, I have no idea about that. I sit in on, I'm in the Department of Medicine, and I listen to the MDs and all that talk about that all the time, and I have no idea what they're talking about, but I'm just a lab researcher. But I do think that things like AI, so I heard an article the other day about AI and reading of CT scans and MRIs and things like that, and how it's going to make the radiologist's life a lot easier, because I heard that the false negative rates are really low, but the false positive rates are high if you use AI to examine some of these scans. And so you're not going to get rid of radiologists and people to actually sit there and read it, but you could reduce their burden and get patient results quicker. So I know you didn't ask me anything about AI, but that's the last thing I heard, and I think that was interesting for me. So. Yeah?
Is pancreatic cancer cured?
No. I mean, still, we're only at a 9% 5-year survival rate, and whether or not this trial is just going to, the article said the trial is about to start, but that's going to mean it's going to be a phase 1 trial, which is going to take a couple years, and that's only going to be 6 patients. And then it's going to be a phase 2 trial, which is going to be 100 patients. That's going to take another 3 years. And then it's going to be a phase 3 trial. And so, I mean, we're way far from that. And I don't, like I said, I would imagine that type of vaccine technology is only going to be useful for a subset of the pancreatic cancers. I mean, I hope it's more broadly useful, but I don't see it yet. It's a wait and see, but it's a step. Like I said, any way we can push that survival curve just a little bit to the right, especially in pancreatic cancer, is huge for the patients. Yeah. I'm sorry? Oh, a maximum that our immune systems can learn. Huh. Well, I mean, you definitely can overstimulate. That's where you get autoimmune diseases, right? So there's a very fine line between too much activation and not enough activation. And that's what these immune checkpoint therapies I was kind of talking about before, where the tumors find ways to turn your immune system off. And actually, one of the side effects of some of these immune checkpoint therapies is you're trying to turn the immune system back on to kill the cancer. And what happens is, within the tumor, you have these immune cells, and they're turned off. But in the rest of the body, you have your normal immune cells. And so now you give this immune checkpoint therapy, you turn the immune cells on in the cancer, but you also turn them on in other parts of your body. And so now you can get things like kidney disease and other autoimmune diseases because of that off-target side effect. So nothing is perfect, but as far as if you can educate your immune system, yes, there has to be an upper limit of what they can do, but I don't know what that number would be. It would be a huge number of things that antigens or things that your immune system could identify and kill for the rest of your life. We just don't know that yet. Yeah? Sorry. One more. Right here. Yeah, okay. I mean, and then this is always, so the question is about, we're talking about therapies after you've already had cancer. But the question is prevention, and this is always something that we always discuss. Researchers, should we put the money into therapy? Should we put the money into prevention? Because people are getting cancer now, but can we prevent them from getting the cancers 30 years from now? And the answer is, yeah. I mean, the estimate is if there was no smoking, no drinking of alcohol, and no poor diets, you probably get rid of 60% of all cancers in 50 years, 60 years, right? So the next generation, starting now, if there was no smoking, no alcohol, and no bad diets, the cancer rates would plummet. So that's the easy answer. I mean, we've already made roads for the smoking stuff, but everything else is, lifestyle choices. I mean, lifestyle choices are by far the #1 cause of cancer. So, some questions over here? Yeah.
Have you had discussions about how the NIH Reform Act could affect research and grants?
The NIH what?
The NIH Reform Act that's going through Congress right now?
I don't know anything about it. I try to stay out of that politics. I'll take one more question. Somebody else maybe, and then I will answer any questions that anybody has up here all night long if I need to. And no more questions over here? Yeah.
How do you keep up with all the research that's being published? What's your technique?
Yeah. How do I keep up with all the research that's published? I don't. I mean, I used to be way better at it. When I only had to worry about my research, I knew everything there was to know about my project and my stuff. But, you know, as you get more important and you have way more administrative duties and you're in charge of running all kinds of other people, then I try to rely on my graduate students and my scientists and stuff to bring me the interesting stuff. I tell you, when I was a grad student, I got table of contents to like a separate email account from probably 100 journals. And I would at least read the table of contents of those, whether or not I open the articles or not, but now I can't tell you how often I actually read papers. It's so difficult too right now. Like, one of the things that's happened in research recently is there are so many online-only journals. Like, you used to have to publish in an actual journal. Like, it would get printed and get sent to all the scientists in the world, and they would read it. But now, you can publish anything somewhere. And that's the problem too, is 80% of stuff that gets published is absolute BS. And I'm going to end right there, but I will answer any other questions. Don't forget to close out your tabs with Olivia. Take care of her. Thank you. Come to the next Beer of the Scientist.